lab this week is fairly mellow. You're going to use a voltmeter, measure some potential differences, figure out some electric fields from it. And those of you who didn't finish the computational lab last week will have time to finish it at the end of this week's lab with help from our intrepid TAs. So that proved to be just kind of a little bit too big a chunk for one lab, and sorry about that. So it's fine to finish it this week. I would like to show you something that might make your life easier, and those of you who did finish the lab might actually like to think about taking 3 minutes and doing this. Okay, so you need to be able to see this on blank. Go away, glow script. Okay, so here is, you can't see it, but here is a program that actually does what you needed to do last week to make a drop orbit a knitting needle. Okay, so you have to calculate E every time through the loop. You've got this whole nested loop thing, and it actually does make it possible to have some cool orbits. So, okay? But there's kind of another way to organize the program that actually is just a little bit easier to read and understand. So here's a program that does exactly the same thing, but notice how different the loop looks here. So we get the net electric field at the location of the drop, and then we get the force, update momentum, update position, update time. But instead of having all this code in here to calculate E, we have a function. What's a function? Well, you've been using functions for a semester and a half in VPython to do various things. So anything with parentheses in it is a function. So sine of x is clearly a function. Sine of theta is a function. But when you were doing of some vector r, you're calling a function to get that magnitude. So if you said r mag, what does that function do? Well, over somewhere, this happens to be one that's provided for you by VPython. So somewhere there was something that said def magnitude of my vector, and it said m equals square root of my vector dot x squared plus, and then it said return m, and so it does this calculation and then just gives you back the value. But what? There is a colon. But you could have made this function yourselves. Okay? And the rules in Python are functions have to come at the beginning of the program. So here's what I did to make this function. I said I defined a function called CalculateE, and the information that I give the function is the location where I want it to calculate E. And then it goes through this whole thing. It initializes x and initializes this vector E and loops through all the sources, adding up calculating DEs and adding them up. And when it gets all done, it says, I know what that is, and it says return E. So that down here, all I have to say is ENet is calculate E where at the current position of the drop, and then it goes and does that and brings it back. It makes your code much cleaner and easier to read. And it makes it modular, so you can debug pieces of it one at a time. So this is kind of a nice thing to do. So if you, and we're going to find that this is going to be useful to us because we're working with lots of charges and having to calculate E's or B's or something like that, magnetic fields. So you might think about doing this if you've already got the program working. Even if you don't, you might want to do this because it might actually make your life a little bit simpler in putting it together. And I'm sorry I didn't get together a pre-lab on functions. I'll try to do one after the test so you can actually go back and look at this. But it's a thing that it's a computational idea that we haven't really needed up till now, although we could have used it. Last semester when we were calculating gravitational forces, we could have made a function calculate F grav or calculate F electric or whatever, F spring. So we could have done that, but we've gotten to a point where this may actually make our lives significantly simpler. Now, if you're an expert programmer, and this is really only for expert programmers. If you're an expert programmer, I'll warn you that if you get really fancy, you're going to have to worry about things like global and local variables. But we're not, if you do something simple like this, you just don't have to worry about it, and it'll be fine. So anyway, you might want to try that. You'll have time in lab to mess with it. Okay. So what are we doing today? Well, we're talking about electric potential. And last time we defined potential differences as the sum of minus E sub x delta x plus E sub y delta y plus E sub z delta z, which can be expressed as the vector dot product E dot dl, where dl is our displacement. And we're using dl for displacement because there are too many r's when we calculate fields. L, we use a script lowercase l because if you make it a printed lowercase l, then it looks like a 1, and then it's incredibly confusing. So we need to use a script lowercase l. So what are we doing today? And so we looked at this in regions where we had a uniform electric field. So the electric field didn't change in magnitude and direction along at least one segment of a path. And the question that was raised last week is, well, what if the field isn't uniform? What if it's the field of a point charge or something like that, and it's varying? And so what we're going to do today is talk about potential difference if the field is not uniform, if it's actually varying along our path. And then we're going to talk about what potential at a point means. Now, up to now, we've talked about potential differences, but even the notation suggests that the potential at location B has some meaning, and it does. So we'll talk about what that means. And then we'll apply potential differences to talk briefly about potential differences in locations such as, regions such as inside a conductor or inside an insulator. Okay? Now, one of the things we noticed last week is that, before we get started, that in a situation where we had a uniform field, say it's this way, and we have a bunch of locations that we could take a path if we wanted to calculate potential differences. So here's our segment VB minus VA. So it's always final minus initial. The path goes from the initial to the final location. We knew how to do that. And in this particular setup, and is this going to be a positive number or a negative number? This is the way we've drawn this, VB minus VA. Is it positive or negative? It is negative. We're going, the path goes in the same direction as the field, so dx is positive, e sub x is positive, and then we've got that minus sign. So it's negative, okay? So this is something you actually want to internalize, that if the path goes in the direction of the field, the potential is dropping. Delta V is going to be negative. You're going downhill. So delta V was less than 0 here. For this path here, potential difference is it's 0 because we're going perpendicular to the field, and so there dx is 0, so ex delta x is 0. Ey is 0, so ey delta y is 0, so it's 0. And we saw that that gave us the same result as if we'd actually gone that way, because the only non-zero component was this x component here. C to D in this region, is that going to be positive or negative potential difference? That one's positive. And if we go from D to A, yep. And what do you think if we took this whole path, what would, it should add up to 0, right? And even the notation suggests that VA minus VA had better be 0. And if we work it out with numbers, that's what we're going to see. So we can make up some simple numbers. So this is 500 newtons per coulomb, and let's say this distance is 1 meter, just to make our lives simple. Okay, so VB minus VA would give us a minus 500 volts, right? We already know that's 0. VD minus VC, I'll write it the other way. Well, we have E sub x is 500, delta x is a negative 1, so minus 500 times a negative 1 is going to give us a plus 500 volts, and that's a 0. So the potential differences do add up. And this turns out to be a very general thing. Even if the field isn't uniform, and there is the field of in a non-uniform field, and even if the paths curve, which is legal, the round trip potential difference is always going to end up being 0. And that's a very general thing. Okay, so let's talk about varying fields. So the simplest case of a varying field is the field of a point charge, which falls off like 1/distance squared. We know that, right? So suppose we have a point charge here. And we have some initial distance. Let's say we're going from, this is This is our initial location, this is our final location, and we're just taking a path that moves in radially like that. We can't just take the length of the path, delta L, and multiply it by the electric field, because the electric field changes over the path, right? So we could get an approximation if we said, well, we could calculate the electric field here and say that's some sort of average, and we could multiply that times delta x. But that isn't a great approximation because it's not changing linearly, is it? It's falling off fast with distance. So what else could we do? We could take smaller steps, right? So we could say, well, we could divide this path up into lots of little pieces. Delta x, and we could calculate the electric field. So we'd have an E1 here, and an E2 here, and an E3 here, and an E4 here. Okay, so we could take E1 times delta x minus E1 times delta x plus a minus E2 times, okay, so we could do that, right? And if we had a path going the other way, we could do the same thing, right? So if we had, this was our initial location and that's our final location, we can take lots of little steps here and calculate E at each point. So what we're going to get is delta V is the sum of minus EX delta X, EXI delta XI, the sum over I. So we're going to add up all those little, okay? So we could do that. And we could do that if we wanted to take the time in this class. Everybody could take a little segment. We could make up some numbers. We could calculate that. Okay. And that's the most general thing we can do. So the first thing so we have a procedure that looks a whole lot like the procedure we had for calculating the electric field of distributed charges. So it's a little different because the first step is choose a path. Now, how do you choose a path? Isn't that overdetermined? Well, it isn't, because even in the situation where we had a uniform field, so here was our uniform field and we had location E. There were two ways we could calculate these. We could choose this as path 1, or we could do that. And that was simpler because this was easy to calculate and that was 0, and so that was, but it comes out to the same either way because the round trip potential difference has to be 0, so going the other way has to add up to those two, right? So we choose a path that looks convenient, and that's a useful thing. And it's a good idea to draw E and delta L along at least of the path. So here's our path. I'm going to draw delta L, and I'm going to draw the electric field here. And that's another way of just kind of recording information that we're going to need on the diagram. Once we've done this, it suggests that at least for this step, the potential difference ought to come out to be negative because the path is going in the same direction as the field. Now we want an algebraic expression. For delta V of one piece of the path. So how do we get an algebraic expression here? Well, to get an algebraic expression, we of course need a coordinate system. So let's put the origin at the center of the point charge. And we'll say that this distance here is x initial. And we'll say that is x final. We're working in one dimension, so we can use x. R would, of course, be a more general thing, so we could use r if we wanted to. So for one segment of the path here, well, that's going to be a minus ex delta x. And here we actually have an algebraic expression for E. It's not a number, right? It's not E is 300 volts per meter, but we can write it as a function. Because what's the electric field of a point charge? So we have a 1 over 4 pi epsilon 0. We have Q of the point charge. And what's our variable here? Variable's just x. So wherever we are, that's x. So we have an x squared. So that's the E sub x piece. And then we have the delta x piece. So that's a delta x. So that's our algebraic expression. And the way we've written it here suggests that we probably, in this case, can just turn it into an integral. And just integrate, right? And do it with calculus. So the next step is add it up. So let's see if we can convert this into an integral. So this was delta V of one piece, but we want all of them. So what we're going to end up with is an integral delta V equals minus the integral of E sub x dx. So it's minus the integral of 1 over 4 pi epsilon 0 Q over x squared dx. And what are our integration limits? Because we've got a path that has a beginning and an end, so this is a definite integral. X initial to x final. Now this is an integral that we can do. Delta V is minus the integral of 1 over 4 pi epsilon 0 Q over x squared dx from x initial to x final. So we have a minus 1 over 4 pi epsilon 0 Q times the integral of x to the minus 2 dx from x initial to x final, right? So what do we get here? What's the integral of 1 over x squared dx? Yeah. So we have 4 pi epsilon 0 q times a negative 1 over x from, we can check that by differentiating, so d dx minus x to the minus 1 is going to be minus a minus 1 x to the minus 2, which is x to the minus 2, so that looks right. And so we get a 1 over 4 pi epsilon 0 q times, so these two minuses cancel out. We have a 1 over x final minus 1 over x initial, right? Now, does that have the right sign? We're going away from the charge, moving in the direction of the field, so our answer should be negative, shouldn't it? Is this a negative number? It actually is negative, because if x final is 100 and x initial is 10, we've got a small number minus a big number here, so this whole thing comes out to be negative. So, of course, what's step 4 going to be here? Yep. Check. And so that was one of our checks. Is the sign coming out right? What's another obvious check we should do here? Units. Units. So we have Newton meters squared per coulomb squared times coulombs times 1 over meters, which gives us Newton meters per coulomb, and a Newton meter is a joule. So that's joules per coulomb, which is volts, so we're good. So often we can, in a case where there's a varying field, we can just be a little bit careful and set up an integral and do it analytically and get an analytical expression, which is valid, which we can apply to any actual situation. So if we have if we say that this is 3 nanocoulombs, and this is 2 centimeters, and this is 20 centimeters, then we could get the potential difference here is going to be equal to 9 times 10 to the 9 Newton meters squared per coulomb squared times 3 times 10 to the minus 9 coulombs times 1 over 0.2 meters minus 1 over 0.02 meters. Then we'd get the potential difference, right? Okay, so what we actually did here is we actually said that the potential difference was minus the integral from some initial value to some final value of an E dot dl, basically, where dl is steps along our path. So delta L is that vector. So dl is so that could be a more general definition of potential difference. Does it work for a uniform field? What if the field is uniform? So then we get the integral from some initial value to some final value of 300 newtons per coulomb times dx, which comes out to 300 newtons per coulomb times dx from initial to final, so that comes out to a minus 300 newtons per coulomb times x final minus x initial, and that's exactly what we were using before, right? So this is a more general definition of potential difference. It includes the definition we were using for a uniform field. Questions so far? So, could you apply this approach with an integral to, say, the field of a dipole? So the question is, can we write the field of a dipole as a function that we could integrate? Yeah, right, it's 1 over r cubed with some constant. We could do that for a field of a dipole. Can we do it for the field of a charged rod, a uniformly charged rod? Yeah, we could, right, because that was a 1 over r, right? So there are a lot of situations where we can just use an integral. And then there are situations where we can't. And we'll have to do it numerically. But so one last, before we start applying this to solve problems. So what does the potential at a point mean? And obviously must have some meaning, but how do we calculate the potential at some point? So what is V sub B? Well, it turns out what this means is it means that it's the result you'd get if you started infinitely far away and walked along a path to location B. So here's our point charge, and here's location B, and we want to find V sub B. So we start over here at infinity. And we march along this path, integrating E dot dl, E dot dl, E dot dl until we get to b. So it's minus integral of E dot dl from infinity to b. So what is that according to our result here? That's going to give us a 1 over 4 pi epsilon 0, whatever our q was, times 1 over, we'll call this distance r sub b, so 1 over r sub b minus 1 over infinity. And being physicists, we believe that 1 over infinity is a perfectly good number. We think it's 0. So that it gives us 1 over 4 pi epsilon 0 q over r sub b. Now, is this consistent with anything we already know? So what would, suppose we made a potential energy problem instead, and we said we have a system of two charges here. So this has a charge q, we'll call that q1. And here's a charge q2, which starts out infinitely far away, and it moves to a location b, which is a distance r sub b away. So the change in electric potential energy of the system is just q2 times the difference in potential between these two locations, right? So that's going to give us a q2 times 1 over 4 pi epsilon 0 q1 over r sub b. In fact, minus a q2 times 1 over 4 pi epsilon 0 q1 over infinity. And this sure looks like our expression for electric potential energy from last semester, right? We had a 1 over 4 pi epsilon 0 q1 q2 over r was electric potential energy. And this is consistent with the fact that electric potential energy goes to 0 as we go out, the separation between the particles gets to be infinite. So this is completely consistent with what we were working with in terms of potential and electric potential energy last semester. Okay. All right. Let's look at some applications of potential that are kind of interesting. So let's consider. So let's write our definition of V at some location. It's the integral and that came out to So let's consider a problem of the following kind. Now this a region of non-uniform field, but it's actually sort of piecewise uniform. So there's several regions, okay? So here's our problem. We have a capacitor and this distance is, and these plates are really big, this distance is and the potential difference here is from a path that starts here and goes to there is 6 volts. Okay? So what's the electric field inside this capacitor? Okay, this is not a hard problem. What is the electric field inside the capacitor? Yeah, right, exactly. So delta V is E sub x times delta x, and we actually already know the direction the field has to be going, right? So what direction? Yeah, okay, so the field has to be going this way because we know. So therefore 6 volts is minus something times 0.003 meters, and in fact that something has to be 2,000 newtons per coulomb, 2,000 volts per meter, right? Okay, so E is equal to 2,000 volts per meter. Okay, so don't forget everything we did already just because we did some integrals today. Okay, questions about that? Yes? Wouldn't it be negative 2,000? No, because actually delta x is negative, right? Because we're starting at a bigger location and going to a... So on physical grounds, you can get the sign. It's got to be positive because we're going... And so being careful, E sub x is greater than 0, but delta x is less than 0 because we're going from a bigger, larger to smaller location. So it's a good question. Now, okay, so we know that E is 2,000 volts per meter. Now, you put inside the capacitor a block of metal. So this is a block of aluminum. It's neutral. And it's 1 millimeter wide, and it's big. It goes, okay? So now what's the potential difference from here to there, or the other way around, the same way we did it before. Well, that's an interesting one because some changes happen, don't they? So, in order to figure this out, we'd have to know the electric field here, and the electric field here, and the electric field here. So, now do we know any of those fields? So what happens when we put this block of capacitor? It polarizes. It does polarize. And so we're going to have the mobile electron C shift so that we've got negative charge here. We've got positive charge here. And it polarizes until what? The net electric field inside is 0. So E net 0. Okay, so actually we do know the electric field in one region. We know that the electric field is 0 inside this block of metal. Now there's but the question is, we now have a whole bunch of other charges, so what on earth are E1 and E3? And there's kind of an there's kind of an interesting way of looking at that. Because as Charles suggests, this sort of looks like a capacitor, actually. And so does that. So if we could somehow figure out how much charge is here, then we might be able to figure out the field here. So we'll call this a minus Q1 and a plus Q1, and if we knew the radius of the disk, we could calculate that charge from the field. Okay. Oh, I totally forgot to do this. Let's do this. Sorry about that. So as one of you said, the reason the net field in here is 0 is that this is the superposition of two fields. This is E of the capacitor, and this is E of the metal. And they add up to well, doesn't that mean that these charges, which kind of look like a capacitor, are making the same field as those charges, which look like a capacitor? So maybe, in fact, this charge, which we'll call Q2, has to be equal and opposite to that charge. More formally, we'd have the magnitude of the field of the capacitor is Q1 over the area of a plate over epsilon 0. The magnitude of the field of the polarization charges on the metal is equal to Q2 over the cross-sectional area, the surface area of the plate over epsilon 0, but that we made the plate the same size as the capacitor. So those areas are the same. So it looks like for these things to be equal and opposite, Q1 has to equal Q2. Now we are making the approximation that these, or the assumption that these all these distances, the radii of these things are so big, are much, much, much bigger compared to 3 millimeters, right? Yes?
Why are the areas the same?
Why are the areas the same? Because we made them the same. To make the problem easier. If it wasn't, we could still figure it out if we knew the ratio of the areas, right? So if we if we knew that this was shorter, and so the area of the metal plate was half of that area, we could still figure out the amount of charge, right? But we're making it simple by okay. So now what do we know about the electric field in these gaps? It was 2,000 volts per meter. It's still 2,000 volts per meter. Because here are these charges. So we still have a field of so we have a Q1 and a plus Q1 and a minus Q1 and a, okay? And why can we make this assumption? Well, we're ignoring what we called the fringe field of the capacitor. Okay, so remember when we talked about capacitors, so we said in here E was Q over A over epsilon 0, and out here we did have a non-zero field, but it was quite small, and it was something like Q over A over epsilon 0 times, I think it actually came out to be the ratio of the separation between the plates over the radius, but I'm not exactly sure what I could look it up. But 3 millimeters compared to 3 meters is 1,000 times smaller. So okay, the field out here is 1,000 times smaller. And so, yes, the field here is the field of these charges plus the field of these charges, but that field is going to, out here, is going to be 1,000 times smaller than this, yes.
So if we were calculating the electric field, why would it be equal as opposed to different, because delta X is kind of different if we're going from the plate to the aluminum?
Okay, so the potential difference, so that's the next step, right? So the electric field actually in this region didn't change in magnitude, and in this region didn't change in magnitude, and in this region it went to 0. So now you're right, the next step is to calculate the potential difference across the capacitor. And for this, so here we're back to a situation where here's our path. But along this path, the field isn't uniform. Now, it's sort of piecewise uniform, but it's not completely uniform. So what do we need to do to calculate this? Yeah, so we just break the field, the path up into 3 steps. Instead of, this time we don't need an infinite number of steps, we just need 3, right? Because it's uniform here, so that's our first step and that's our second step. So we add some new locations of our path, which is fine. So we would call this delta V3, and we'd call this delta V2, and we'd call this delta V1. So we have delta V1, delta V2, delta V3, and delta V total. Okay, so which one's easy? Which one can we just do by inspection? Yeah, delta V2 is 0, isn't it? What's delta V1? Okay, so we have a minus 2,000 volts per meter times a negative 1 millimeter, right? Which gives us 2 volts. And down here we have a negative 2,000 volts per meter times negative 1 millimeter. So we have another 2 volts. So now this is 2 volts plus 0 volts plus 2 volts is 4 volts when it was 6 volts before. So a lot of stuff went into that. There are probably questions. Is it always going to be 2/3 of the original voltage? Well, the key thing is for what fraction of the path is the field now 0, right? So if this was bigger, so we used a lot of from chapter 14, which is that a conductor at equilibrium in the presence of an external field polarizes in such the way that the net field inside goes to 0, because if it doesn't, charges keep moving and it's not at equilibrium. We used what we knew from chapter 15 about the field in a capacitor, and then the quote fringe field of a capacitor, the field outside a capacitor, to reason about what the fields had to be in here. And then we divided the path into 3 steps because there were 3 regions where the field was uniform. And we calculated the potential difference. You can let the questions percolate. So how does superposition work out here? So what if we had a charged disk here. Actually, let's do it this way. We have a charged disk that's what? Positively charged. And we have a hollow sphere, like a ping pong ball. It's negatively charged. And we want to find a potential difference. We'll call this location A, and we'll call this location B. So we want VB minus VA. What's our plan? What's our plan? How are we going to approach this? We have two sources of field. What? Yeah, it's their, yeah. So therefore they're insulators, because if they weren't insulators, they wouldn't be uniformly charged. And so this is some distance d. And the radius of this disk is much greater than d. And this, so we'll call this a minus q1, and the radius of the sphere, this little sphere, is r1. This is, we'll call that a q2. We'll call that an r2. R2 is bigger than the. So I just want to plan. How are we going to do this? Okay, so do we have to get that complicated though? I mean, we could divide the sphere into rings and things like that, but what do we know about the electric field of a charged sphere? Zero where? Inside. So E1 equals 0 here, and outside, what do we know? Looks like a point charge, doesn't it? At the center of the sphere. So outside here we'd have, somewhere here we'd have an E1 that declines as 1 over r squared, moving from the center of the sphere. Okay, so we've taken the first step. We've said, well, we're starting to draw some fields. Okay, so let's draw the contribution of the disk. Okay, so the field points, so we only care about the field in this region here. And the field due to this disk points away from the disk, and it's actually uniform. So in here, okay, so we have these two contributions to the net field. So to get this potential difference, so are we going to want to break up our path into different pieces? We are, aren't we? What are the logical pieces to break up the path into? Okay, inside and outside. So we have piece 1 of our path here, and then piece 2 of our path. So inside the sphere, and then we're just going to add it up. So we'll call that location C. We just made it up. So that's VB minus VC plus VC minus VA. Now in here it's simple, right? All we've got is the field of the disk, right? So that's just going to be VC minus VA. We have a minus, we have a minus Q2 over A over 2 epsilon 0 because it's a disk. So that's the x component times delta x1, whatever that is. What about out here? How do we deal with the fact that we've got two contributions to the field? We've got the disk and the Yeah, you can calculate them separately because superposition says the net field is the sum of those two fields, so the potential difference is going to be the sum of the potential difference with respect to the disk and with respect to the sphere. So we can just calculate the potential difference with respect to the disk, which is another, and then it looks like a point charge, and we know the potential difference near a point charge, right? So we're going to get VB minus VC is some constant. So E disk x delta x2 plus the Q of the sphere, which was Q1, 1 over 4 pi epsilon 0 Q1 from whatever this distance is here. So the initial distance is 1 over the radius of the sphere, and the final distance is 1 over, what did I say, 1 over d, right? Yeah, so it's basically just superposition. I mean, but we do need to break the path up into two segments. So you need to start looking at paths. The integrals we've been doing here, the integral we did to get the field of the charged, of a point charge, we integrated along a path. This is, in calculus, it's usually called a line integral. Physicists typically call it a path integral because we're actually taking steps along some physical path, but it's the same concept as if you've seen it in calculus. And we won't ask you to do hairy ones. Either we're going to be doing something that's easy to integrate, like the point charge or a dipole or a rod or something like that, or usually you can tell by inspection what's happening. So we're not asking you to somehow do weird, strange integrals to get this. Okay. Suppose you you went around with your little proton on a spring and you measured the electric field at various locations. So you measured it here and you went around a circle measuring the electric field. So you made lots and lots of measurements on a circle. And you measured the electric field everywhere on the circle, and you always found that it was tangent to the circle. And your friend looks at you and says, "That's impossible." Is it impossible? Can you think of an arrangement of charges that we could make that would make an electric field like that? Think about it for a minute and try to draw an arrangement of charges that make a field like that. You can't have a spinning dipole. It has to be stationary charges. Can you do it? Let's think what would happen if we did succeed in doing this. Suppose we put a proton here. And it starts, so there's a force on the proton, right? So it starts to move, and there's still a force on the proton, so it starts to move and it's moving faster, 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 and it's gaining energy. And where's the energy input to this system exactly? we glued down these charges and walked away. That's not happening, right? So what have we violated that we talked about today by postulating an electric field, a configuration of electric field in space, a pattern of electric field in space? Yeah, yeah, delta V round trip. And what that seems to really refer to is conservation of energy. We can't think of a situation where we could glue down charges or put them on the surface of spheres or disks or whatever in such a way to make a pattern of electric field like this in space. Because if we could, that would actually be capable of giving energy with no energy input. So if we take our round trip path, starts here and goes there, we're going, so delta V is greater than 0, so it's actually impossible. So we've found a pattern of field in space that can't be made by fixed charges. Which is kind of interesting. So your friend was correct, having taken very seriously down to delta V round trip must be 0. What about other things? What about things that aren't fixed charges? Stay tuned.